Okay, so we are on week 5, which means we just have a couple more. We'll just have this week and then week 6 and week 7, and then we will be done with the course. So as a reminder, May 3rd is the last day of the course. So looking at this calendar, we'll meet next week, the 23rd, and then we'll meet May 30th or April 30th, and then that'll be the end. So be mindful of that. That date will come up soon. And yeah, definitely ELT 126 is a prerequisite for a couple courses, I believe, especially those that are going through like the lineman or electrician program. So be mindful of that because I believe you need a 2-point in order to pass this class. So keep up with your amateur modules and reach out to if they're not recording properly. Sometimes they are not recording properly, so I have to manually do them. So okay, so I'm going to share my screen. Pull up here in a minute and see where we are at. So we are on week 5. Congratulations, this is the last week of math. So that's great. So you just have this word problems quiz for week 5, and then you'll see that week 6 is just electrical and week 7 is just electrical. And on top of that, there's only one quiz for both of those. So yeah, so the next 2 weeks too, we'll probably spend some time talking about some of these amateur modules. So just because the week 5, 6, and 7 are shorter. So we'll spend some time. So if you haven't done all those or are having troubles, bring questions. But this week, for the electrical side, talks all about RLC circuits. So you can read all about those in this PowerPoint here. This is a pretty long PowerPoint, if I remember correctly. I'm gonna pull it up and see, because it goes back to using that Grob's book, it's called. So they're kind of long, but we'll kind of talk through these. Essentially what these are, we have parallel reactance and resistance circuits and then series parallel reactance and resistance circuits. So it kind of combines the last 2 weeks together. And I will say that this is confusing to read through, which is why I never talk through this. If you follow this, that's great. But if you don't stress too much because it is confusing. So I think the best way to do it is the way that I'm going to talk through week 5 is I took a couple screenshots of the video that Eddie Burkhead does, and I'm just going to kind of slow it down and we're going to break it down because the videos this week are really thorough and like the concepts that you're supposed to know. So we'll just kind of break it down and make sure that it makes sense to you. And if it doesn't, we'll stop and re-explain it. I'm going to turn off my camera here too, because sometimes it goes down. Okay. So just a couple ideas from week 4, when we talked about parallel circuits and resistances and reactances and inductive reactance and all of that. So this is an example problem from last week. So let's say we had a 120-volt parallel circuit with 3 branches. Hence, it technically didn't have to say parallel. You could have assumed that because of the fact that it has 3 branches. And you have 2 resistors with resistances of 60 and 120 ohms, and an inductor that has an inductive reactance of 30 ohms. Then it wants us to find the total current on the circuit. Be mindful that it says total current and not total resistance, because now we know there's going to be a couple steps here because we don't know what total resistance is. So that's step 1. Because technically, I always think about it when you're solving circuits, there's 3 things normally that you need to find. And regardless of what type of circuit it is, you're going to need resistance, total resistance. You're going to need total voltage, and you're going to normally be asked for total current. Actually, that's the process to get there. It's different depending on what your circuit looks like. So in this example here, you'll want to find the resistance like normal for parallel circuits, which is using that equation where you multiply R1 times R2 and then divide by the sum. So in this example here, we have 2 resistances, 60 ohms and 120. So you multiply by itself and divide it by the sum, 120 plus 180, or 120 plus 60 is 180. If you do the math there, it gives you 40 ohms. And this should be a topic that we learn in 120, right? Where it was that, as a reminder, we're looking at this equation, just so you remember, it was RT equals R1 times R2 divided by R1 plus R2. This is the equation for finding total resistance for parallel circuits. There's a more confusing equation if you have more than two, but there's only two, so we just need that one. So that's the first step. Step two, you can find that's, oh shoot, sorry, I didn't mean to do that. Sorry, 1 minute. Okay, you should see it now. So step two is finding the amps here. So you can do that by just using Ohm's law, because we know 120 is our voltage and 40 is our resistance to give us 3 amps. So that is the current at the resistance. We can also do the current where we have the reactance, right? Because we where we have the inductor. So it's 120, which is the voltage, divided by 30, which is the resistance, not really the resistance, but the reactance. That gives us 4 amps. So once we have both of those, you can use the Pythagorean theorem to essentially find the total current. So that's, again, from last week, where we did the square root of 4 squared plus 3 squared equals 5 amps. So this is just a recap of last week. So this equation should also look familiar, just because, again, that's the equation for when we are dealing with inductive reactances. So any questions about this from last week? How you do a problem like this? So again, the total current is 5 amps, but to find the total current, you have to find the current at both locations, because the current does change since we're dealing with a parallel circuit. If this was a series circuit, we would only have one current and one change. Okay, so now getting a little into this week. So total reactance is something that you can calculate, and we'll learn kind of a new way to calculate it this week, but it really depends on if you have a series or a parallel circuit. And that's one of the things you'll want to determine first. And we'll do a couple examples here in a minute. But one thing to kind of like keep in mind, and I'll explain more about this when we do the problem, but this is something you'll just want to write down for now. When we are combining reactances, we use this sort of like up down arrow method. And in it, you have to remember that in a series circuit, inductors point up and capacitors point down. And the opposite is true in a parallel circuit. And that just has to do with the fact that inductors have, if you add more inductors in a parallel circuit, it's going to decrease your inductance. The opposite is true for a series circuit. So this first two bullet, or the second and third bullet, are the most important things to remember for this week, and we'll do examples of what that means in a minute here. Then also remembering the symbol for capacitors and inductors. So I just took a quick screenshot, but like if you, we'll draw it better here, but like if you see in a circuit where you have like these two plates, this is indicative of a capacitor. And then if you ever see this coily line, that's indicative of an inductor, which makes sense because we talked about like how capacitors like those two plates and how inductor is just like a coil of wire. So it makes sense that that's what they look like, but just be mindful of that because you'll see that in a minute here. Okay. So now an example of what this up-down means. So let's say the first thing that they do, and I don't know what video this is, it's from other videos from this week, but he drew a circuit where he had, we know it's an AC circuit because there's symbol here. You had a voltage of 10 volts, and then they drew a capacitor, and they said it had 15 ohms, and they drew an inductor with 5 ohms. So the idea here is we want to essentially, similar to 120, where we were, you remember in 120 how we had one circuit and we simplified it, right, and drew a different circuit? That's what we're doing here. All we're doing is simplifying this circuit and combining the reactances together, so we just have one value. So you can combine reactance, capacitive reactance and inductive reactance together, and you use this up-down arrow method to do that. So essentially, again, we have the circuit with a 15 ohm capacitive reactance, 5 ohm inductive reactance, and you essentially want to find the difference of both of these. But depending on if you have a parallel or a series circuit is going to depend on if you have more capacitive reactance or inductive reactance overpowering the other. So since we are dealing here with a series circuit, in a series circuit, inductors point up and capacitors point down. Inductors point up and capacitors point down. Yes, so inductors point up. So when you draw the arrow, since we're doing with a series circuit, you would draw an up arrow and put 5 amps, and then we would draw a down arrow and put 15, or not 5 amps, 5 ohms, and put 15 ohms on the down arrow. And again, this is because going back to this, we're dealing with a series circuit, and it says inductors point up and capacitors point down. The inductor here is 5, right? Right here it's 5. The capacitor is 15, so the capacitor points down. And then you essentially look at this and find the difference. So like look at this, you can see like what's overpowering, right? If we have 5 up and 15 down, if we were to combine those, we would have 10, we would have 10 down, right? And that's just because 15 is greater than 5. So it doesn't mean we have a negative, it just means that essentially we have more capacitance or capacitive reactance. And so that's why when they've redrew the circuit here, now we just have it as 10 ohms of capacitive reactance. You can see that there's that capacitor symbol, and that has to do with the fact that once we drew these arrows, we saw which one was overpowering. That's the word I like to use. And again, we know this because going back to this. So to recap, a series circuit, inductors point up and capacitors point down. So when you do this arrow method, you will want to have your two values. You're going to have an up arrow and a down arrow. And in this situation here, the 5 ohms of the inductance points up, the 15 ohms of the capacitive reactance points down. If you do the math here, you can see that like essentially I find the difference of 15 and 5, and whatever one's bigger, that's the way your arrow points. So that's kind of the method that I would do. So this here is an equivalent circuit of this circuit, but now we don't have any inductive reactance. We just have capacitive reactance. So this is like an equivalent circuit to this one. So any questions on this? Because I know it's kind of confusing, but I think it's just good to kind of break it down and see what's happening. And we'll do an example here in a minute for a parallel circuit where we redraw the arrows. But in this example, we'll have to write them differently. But are any like questions about how we went from this circuit to this circuit? So again, all we did was combine these two terms to create an equivalent circuit, and to combine these two terms, we use this arrow method. I'm hoping that makes sense because it can be confusing.
Just to understand it, if it was reverse, the numbers were reversed, like 5 ohms capacitor versus the inductor, it would still be 10.
Yep. But we would have, so you're saying if we had, I'm just gonna like write it on this, so I don't confuse you. You're saying if this was 5, so we had 5 ohms of capacitive reactance and 15 ohms of inductive reactance, right?
Yes.
So so what you would do is it would be 15 here, 5 here. Now instead of we would still have 10, right? Because it's still 10, but now we would have an up arrow because there would be more up here. So we'd have 10 ohms still, but now we would have it in inductive reactance.
Okay, and then it would be rewritten. We would be doing the work with an inductor in the final step 3.
So this would look like this.
So that would be the only, that's what would change. Okay.
Yep. Yeah. So that's why I always say, like, essentially all you're doing is finding a difference between these two to like combine them because they work against each other. So it makes sense that it's like a difference, but you have to determine if you have more inductive reactance or capacitive reactance. You have to, it's easier to kind of just do this arrow method and see what's overpowering. As you get better at it, you'll just kind of start to remember, oh, like, okay, and we're dealing with series circuits, so you'll just remember that inductors point up and all that, but yes, so.
Okay, thank you.
Yeah, of course. And we'll do a couple examples today, so if it's still not clear yet, hopefully it will be. So this is an example here where we have a parallel circuit. So I drew a parallel circuit, AC, 12-volt battery. In this example here, they had a 3 ohm. You see there's a 3 ohm and a 2 ohm capacitive reactance or capacitor, and then a 4 ohm inductor. And then they found the amperage at all of those locations. All they did to find that amperage here was use that voltage. So 12 divided by 3 is 4, 12 divided by 4 is 3, 12 divided by 2 is 6. So that's the first thing they did. And then the next thing you would do is add them together. So you can see here that now we're dealing with amps, right? And that's because we're dealing with a parallel circuit and the amperage changes. So that's the other thing that's kind of different about this. So when you're dealing with series circuits, when you draw your arrows, the values that you use is going to be your, like you're going to do the arrows in ohms, like when you're dealing, like you're dealing with resistance and reactance. So we had 5 ohms and 15 ohms. When you do it for parallel, you want to use the amperage. And that just has to do with the fact that in parallel circuits, your amperage is constantly changing. So that's important. So that's another distinction here. You can see that these numbers that they're using is amps and it's not resistance. So you can see that we have 10 and 3. So where did this 10 come from? Well, this 10 came from the fact that we added the amperage of the capacitors together, right? And you can just simply add them together because it's the same unit. So we had 6 here and 4 here. So that's where this 10 came from. The 3 came from the 3 here. And this, if we go back to this, it's still the same thing. We're in a parallel circuit. Now inductors point down and capacitors point up. So going back to here, the inductors point down. Well, the 3 amps here, the current on that 4 ohm inductor, the current was 3 ohms. So that's going to point down because that's the current at that inductive location. And then our up arrow is going to be 10 amps because that's 6 plus 4. That's our current where we have the 2 capacitors. In this example here, 10 and 3, we have more in the up direction, right? You find the difference, and then more is going to be up. So that's 7 amps. And then we can use that value to find the total reactance. So it's just using Ohm's law again, V divided by I, 12 divided by 7, because that's our total current. That's essentially what you're finding here, to give you 1.7. So this total current, that's the current right here at the start and at the end. So this would be 7 amps. And this would be 70 amps. So again, I didn't write 1.7 because this is the reactance / resistance, but 70 amps is the total current because that's when we did the arrow. So this one's a little bit more confusing. So to kind of summarize again, what we're doing here is, so, and there's a video on this, but like I said, I just wanted to like break it down step by step. So what they did was they drew a parallel circuit. They found the current at each location. So they found the current here, here, and here. And they did that simply by using the voltage and the resistance / reactance at each location. And then we draw our arrows. You can use amperage just like we did resistance in the last problem to determine like what the total current was. And then you can use that total current to find the total reactance. Because that's another thing too from 120, if you remember, to find either total reactance or total reactance, total resistance, or total current, or total voltage, you always need the total of the other 2 values that you're doing. So like you couldn't find total reactance by putting 4 amps here, right? Because that's not the total current. And we'll do another example here in a minute, but does this one make sense too? I know this one's a little bit more confusing dealing with the parallel circuit, because it has that additional step of finding the current at each location. And again, that has to do with the fact that the current changes. In a series circuit, going back to this example here, the current doesn't change, so it's irrelevant. But in this example, the current changes and the resistance at different locations. Okay, so now this is an example of a quiz question you would see. This one's a little bit more straightforward. And we can go back to this problem too if you have questions on this one, because I know it is kind of confusing. But let's say we had a series circuit. So we know it's important that it's series, right? Because it goes back to, that's going to dictate if you have more inductance or more capacitance, right? So we have a series circuit with 60 ohms of inductive reactance and 50 ohms of capacitive reactance. What's the total reactance? Well, this is pretty straightforward. If we know in series that inductors point up, we have 60 with the up arrow, 50 with the down arrow, because that's the capacitive reactance. Capacitors point down. That's a difference of 10, and it's more in the inductive reactance. So the total reactance is still just 10 ohms, but if you were to draw this, right, you would draw it with an inductor symbol because there's more inductive reactance, but the reactance is still 10. So it's essentially just finding the difference. So again, like then there's a couple quick questions like this, so they're pretty straightforward. It's just finding the difference, and if it asks for do you have more inductive reactance or capacitive reactance, that's when you'll have to remember that the arrow method. Okay, so now let's do a little bit more complicated of a problem, and I think this next slide will. Okay. So let's say that we had a 120 volt parallel circuit with two branches, one with a capacitor with 120 ohms of reactance, the other with an inductor with 20 ohms of reactance. What would be the total current in the circuit? So a couple things to point out. We have a 120 volt parallel circuit, that's our total voltage. It has two branches. We have a capacitive reactance of 120, an inductive reactance of 20, and it wants the total current. It's not asking for total reactance, right? So you first will want to calculate your current at each location. That's simple because we know the total voltage and we know the reactance at both locations. So we'd get 1 amp and 6 amps. Going back to this one, that's exactly what we did first, right? We found the current in each location. And then you, similar to what we did in this step, that now we can draw our arrows / find the difference. Since we're dealing with a parallel circuit, you're going to find the difference using the amperage. So the difference here, right, between 6 and 1 is 5 amps. But in this example here, we know that since it's parallel, going back to this, inductors point down, capacitors point up. And it just asks for the total current. So the total current is still just the difference of 5 amps. I'm trying to think of why you wouldn't, I guess, have to worry too much about finding doing the up and down arrows as much when it just asks for like sorry, I'm all over the place, but like in this example here, when it just asks for the total current, you can just find the difference. Like you don't have to really worry about like what's up and down since it's just talking about amperage and it just asks for current. But so again, all you have to do for this problem is the same thing that we did when we drew it. You found the amperage at each location and then found the difference of the currents. And then you can use that, like if you wanted to find reactance here, we could, now that we know total current, we know total voltage, but it only asks for current. So it's just 5 amps. So just be mindful when you're taking the quiz of what it's asking for. So it always helps me to underline it. Like this is asking for current. So we just can stop here because it's only asking for current. If it was asking for total reactance, we'd have to do an additional step, which is the step we did here. We'd have to take the voltage and divide it by the current. You could do 120 divided by 5 to get it, but we don't have to. Okay, so the next 3 slides, we're going to talk about what happens when we add a resistor. But I just want to make sure, any questions so far? How are we doing on time? It's 11:30. Any questions so far on any of this we talked about, or hopefully everything's made sense? Okay, so I'm going to assume everything makes sense. So let me know if we have to go back, we can. We'll keep moving forward, keep plugging along. So let's say now we add a resistor. So now we have a series circuit here. We have a 12 ohm resistor. So remember that's a symbol for a resistor, a 20 ohm inductor, and a 4 ohm capacitor. So this is a circuit with a resistor, an inductor, and a capacitor. So now we're going to draw the arrows in the same way. So since it's a series circuit, our inductors point up. So we drew a 20, the 20 here with the up arrow, 4 here with the down arrow. Okay, so this is the same step. But the other thing to notice here is we still have this resistor to deal with. So the first thing you want to do here is just solve for it, right? So 20 and 4, the difference is 16. So kind of ignore the resistor for now. So 20 minus 4 is 16, and that's in the up direction, right? Because we have more inductance here. So now we're going to kind of use Pythagorean's theorem. And basically what you would do is you would do 12. I'm trying to think of the best way to explain this. Essentially, it's finding our impedance. So if you do the math here, and I think we'll use the math way because that's, or maybe this one, no. Sorry, I have too many slides going on here. Yeah, so you would find impedance using 16 and 12, and this 12 comes from this resistance. So the square root of 12 squared plus 16 squared is 20, and that's where we got the impedance. So basically, you draw your circuit, you figure out what your value is, and then you use that value, so 16, plus the value of the resistance, and that's how you can find impedance. So essentially, I like to think of it as Z. It's that same equation where Z equals the square root of resistance squared plus reactance squared, right? Where this is, I didn't write it all out because I don't want to waste too much time, but it's resistance and reactance squared. And in order to find the reactance, that's what we did here. So the arrows are, combining the arrows is still important because of that step. And then once you have impedance, you can solve for current, just like we did last week, where it's V divided by Z equals I, where Z is impedance, and our total voltage we were given for this problem. I forget what it was, but it doesn't matter. So to recap here, because I know I was hopefully not confusing you too much, but basically what you do, and here we'll make it big full screen again. So to recap here, when you have your circuit with a resistor, inductor, and capacitor, ignore the resistor at first, do the arrows like normal, figure out what that value is, and then that value is your total reactance. And then you can combine the resistance and reactance together by finding impedance, and to use impedance, that's when you would use Pythagorean's theorem. And once you have impedance, you can solve for current or whatever you want to solve for. So this is a perfect example of like combining the last 2 weeks, because the last 2 weeks we talked about finding impedance, but before that we didn't have this step of like combining them. So this is the only new step, is this second square, right? Where we had to actually combine the 20 and 4 to get 16, that 16 there. And I think it might help you here. I'm going to circle like the terms. So this 16 here is the same 16 here, right? And that 16 comes from the 20 and 4, the difference. And then the 12 here, that 12 ohm resistor is the 12 here. So that's why we have 12 here. And this 20 comes from this 20 here, that is our impedance, comes from the square root of 12 squared plus 16 squared, which again is impedance. So I'm hoping this helps you to like draw the numbers here. I'm a visual learner, so. Okay, so any questions about what we did for this problem? So again, summarizing it again, all we did was we had this circuit, we found the reactance, the total reactance, by combining these two terms. Then once we had reactance, we can combine reactance and resistance to get impedance. Once you have impedance, you can solve for current. And that's exactly what we did here. Okay. So there's no question, so I'm assuming all that made sense.
Yeah, I am pondering one question.
Of
Uh,
course.
so when we make the difference there,
Mhm.
is X just a standard symbol for reactance, or is that signifying whether it's the inductor or capacitor that's overpowering?
Oh, good question. So I'd have to look back at our notes, but you can use X as like a standard. X is normally just used as like a standard
Yeah.
concept. I think too, it goes back to, if you remember last week, I think it's like X with a little subscript C and a little subscript L, right? For inductance, if I remember correctly. So technically, in this example here, since we have more inductance, I think the right way would be to have like a little subscript L right here.
Okay, but that's not a major thing of how it's going to affect its reactance is reactance. It's
Right, and it
XL.
really doesn't affect it because exactly, reactance is reactance, and in this next step, it technically, if you have more, um, like they show in the videos, like they'll draw the arrow different or the triangle differently depending on if they have more inductive reactance or capacitive reactance. I don't normally talk with that because I think it's confusing, and you're still doing the same thing of using Pythagorean theorem, and it's not going to change your output. So I think
Okay.
it's kind of a mute point to talk about, but yes, that's
I
technically.
I understand what you're saying about which way the triangle's going, as far as whether it was going down or up. And
Mhm.
I haven't seen how that changes the outcome, the number, because everything is still a positive amps or ohms. I mean, it's just showing where on the wave.
Right.
So I see how you're not wanting us to over stress that factor for just understanding for right now. Got it?
Mhm. And I think they explain that too, because it's kind of like foreshadowing like this whole idea of like the arrows and like what you have more of. But I think the arrows and drawing it like this is easier to understand and visualize anyways. So
Okay, that's helping. Yep.
perfect. Okay. So last problem here I want to do is this is just basically the same thing. So, but now we're just dealing with two resistors, and so you can just add them together. So in this example here, we have a 20 ohm resistor and a 40 ohm resistor, 120-volt circuit is normal. Then we have a 12 ohm inductor and a 100 ohm capacitor. So in this example here, the only difference, and there might be a quiz question on this, is you have to combine this resistance. And you can do that pretty straightforward, right? Because it's just using that 20 times 40 divided by 60. And that'll give you the total resistance. So this is the only difference, but it's still the same concept of here. You can see that they drew the arrows. That's what's going on here. They used 100 pointing down because that's the capacitor, 20 pointing up because that's the inductor. So we have 80 ohms of capacitance. So that's where the 80 comes from, and then the 60 comes from adding both of these together. So 40 plus 20. The reason you can just add these together is I think I said originally you have to do the whole multiplying them and then dividing by the sum, but I forgot this is a series circuit, right? So you can just simply add 20 and 40 together to get 60. So that's how they got 60 here. They got 80 here because that's the reactance. You can find impedance by the square root of 60 plus 80 squared is 100. So that's where the 100 came from. So this problem was the same exact problem of this one. The only difference between this and this is you first have to add 20 and 40 together to get 60. And again, the reason we can just add those together is because we're dealing with a series circuit, and the total resistance RT in a series circuit is just the sum of all the resistors together, right? R1 plus R2 plus R3. So like, for example, just to like solidify your knowledge here, if we were to add a third resistor in this problem, right here, I made it 10 ohms. All that would do is now this, instead of being 60, this would be 70 here, right? Because 20 plus 10 plus 40 is 70. So that's all that the resistors do. When you have more than one resistor, you just have to add them together in a parallel circuit. So pretty straightforward. Okay, now in this example here, I think this is basically the same example, but just to talk about it more and solidify your knowledge. So now we have a parallel circuit. We have a 240-volt battery, 120, or what does it give us? 120, 10, and 40. Those are the resistance slash reactances. 120 for the resistance, 10 for the capacitive reactance, 40 for the inductive reactance. So now we're dealing with amperage, so you'll want to find the amps, right? So that's how they found 24, 2, and 6 by just doing 240, which is the voltage, divided by 120 to get 2 amps, divided by 10 is 24, divided by 40 is 6. Once you have those numbers, you would draw your arrows like normal using the amperage again. So we have 24, because that's our capacitors. Capacitors point up because we're dealing with a parallel circuit. Inductors point down. So we get 18. 18, that would be your total current. Now that you have total current, you can find your impedance here. So 18 and 2, and then you can use your impedance and voltage to find your total resistance. So it's essentially the same setup here. And the reason that this is 2, if you're wondering where this 2 came from, that's the amperage at the resistor. So that's why instead of, it's the same thing as this problem where we had the resistor of 60 here, but instead, since we're not dealing with resistance, because it's a parallel circuit and we're dealing with amperage, that's where this 2 came from. So once you find impedance, using Pythagorean theorem, which technically it's not impedance, would be 18.1, then you can find the total resistance by using that 18.1 amps and the 240 voltage. So really the main things to remember are, depending on, you really have to pay attention if you have a series circuit or a parallel circuit. And if you have a series circuit, you have to remember the point of the fact that in series circuits, inductors point up and capacitors point down. That's important when you're drawing your arrows, right? And then you also have to remember, if you're dealing with series versus parallel, when you're dealing with series, when you draw your arrows in your Pythagorean theorem triangle, you're dealing with the reactance and resistances. You're drawing it with those. When you have a parallel circuit, you want to find the currents first, because that's what the values that you're going to be using. But besides that, like, it's pretty straightforward. And this should help too, because like this, I'm going to put these slides here for you in the chat. The hardest problem you're going to get on the quiz is dealing with basically this, where you have, this is the hardest it'll get, like where you have a circuit and you've got to combine resistors and then also combine reactances and then find, use Pythagorean theorem. That's essentially like the end goal. But there are a couple easy questions that are just going to have you do this, like find the reactants by just finding the difference. So I'm going to put these in the chat because I think that those would be helpful. Just having this. And again, like these, there's the videos this week that explain all of what I explained today, but they talk pretty fast in them, and I wanted to make sure I spent time like actually breaking them down and showing you where the numbers came from. But with that, that was all I had for you. So I'm going to throw this in the chat. Hopefully this helps for like just the understanding of this week and how to do the math. But please, if you want me to go back, we have 15 minutes, so I can go back and re-explain anything, or if this made sense, go ahead and take the quiz and reach out if you get anything wrong and don't know what your answer is. But yeah, go ahead. If there's any questions, feel free to ask them now. I'm just, it might take me a minute, but I'm going to put this PowerPoint in the chat here. So if you want to stay on for that. I know it's some right here. ELT week 5. Okay. So you should see those slides in the chat. They're loading. But yeah, if there's any questions, feel free to ask them now. If there's no questions, enjoy the rest of your week, and I'll see you next week, and reach out if there's any questions or concerns.
I do have a question from last week's quizzes.
Okay. Yeah.
I don't exactly know what I might have goofed up on, but I know I took the quiz twice, and the second time I ended up getting one wrong. I didn't. So the first time, so I feel like I wasn't very clear on some of the concepts. I think I'm doing pretty good with the math. It is just the idea of understanding the terminology. I think that